Okay, so I just want to take you through two very simple, very easy algorithms, but they are also similar but kind of important. Okay, so two problems about scheduling or arranging different activities according to a certain requirement. That is the question. So, two algorithms. The first one is what is called activity selection problem. Okay, so I will write this and you have a look at it, you study this, and then this question is also there in your assignment. So I will expect you to write this down after understanding what this is. Okay, so what is the activity selection problem? This is the correct, very good example to look at this is to think about classroom and lectures. Okay, so imagine that you are in a college where there is only one classroom. Okay, and then there are lots and lots of lectures to happen, and you have to arrange, you have to form a timetable, right? So how will you arrange the lectures? What timetable will you form? That is the activity selection problem. Okay, so what does this look like? We are given n activities. Let's call this A1 to n, n activities. But what is important here, every activity has a start time and a finish time. Okay, so each activity AI has a start time SI and a finish time SI. Okay? And now we are going to think of these times as elements on the real number line, as real numbers. Therefore, we will always assume that the activity AI occurs in the time interval closed interval Si to open interval Fi. Okay? So the time instant Fi is not included because we have real numbers, so we have to be careful. Okay? So closed interval Si to open interval Fi. Okay? All time instants between Si and Fi, including Si. Okay, so we will assume that the activity AI occurs at the time interval Si. What else? Further, we will assume that the finish times are sorted in ascending order. Okay, they could be sorted in descending order. The algorithm will be very, very similar. Okay, but just for convention, we will assume that they are sorted in ascending order. What does that mean? That means we have F1 less than or equal to F2 less than or equal to so on to Sn. Right? So how simple? So this is like one lecture hall, n many lectures A1 to A1. Each one has a start time Si and Fi, right? And now the finish times are all ascending. They are all sorted. Okay, so we relabel so that they are all sorted. So we assume that F1 to Fn are all increasing. And now, what is the goal? So the goal is to accommodate as many activities as possible. Right? As many activities are as possible. So why cannot we accommodate all possible activities? That is because sometimes two activities may intersect, right? So one thing here is it's like lecture hall as the example. So you cannot have two different lectures happening in a lecture hall at any time instant, at any common time instant, right? So what is the restriction? The restriction is that two activities, let's call this AI and AJ, are compatible. So we call this compatible in the sense that both of them can occur in any schedule. Okay, so both of them can occur in a schedule. If and only if, what does that mean? The intervals Si and Fi and Sj to Fj do not intersect. Understand? Now, depending on whether Fi or Sj, which one is lesser or greater, it means the start time has to be ahead of the finish time. Yeah. So they cannot intersect. These two intervals cannot intersect. Only then can you have. So two lecture complete duration slots cannot intersect. Only then can you have a lecture in the same lecture hall. Same condition. Okay. So the intervals Si, Fi and Sj, Fj should not intersect. So if Fi is less than or equal to Fj, then what you're really looking for is Fi less than or equal to Sj. Or Fj less than or equal to Fi, then you're looking for Fj less than or equal to Si. Okay. So technically they should not intersect, then both of them can be accommodated in the same schedule. And we say those two activities are compatible, right? So we can only accommodate activities as far as they are all pairwise compatible. Okay, they will not always be compatible, but we try to accommodate as many as possible. So how to solve this? Solving is extremely easy. We solve this greedily, and this is the best way to solve it. Okay, but that proof we are not interested. We are not interested in proving that this is the best way possible. We are interested in seeing how it is to be done. All right. All right. So let's continue. So how does this proceed? So the algorithm, not writing the algorithm exactly, I'll first describe what the algorithm is. Okay. Note that there are n activities, A1 to AN, right? Let uh, let's say some set S or T be an empty set. Okay, T is an empty set, but we will keep adding activities to it. Okay, where we will add activities that can be accommodated. Okay, sequentially. If you can add one activity, we'll take T union that and think of that as T. Okay. So what is the first thing to do? First, simply assign T equal to A1. You know why? Because the finish time of A1, F1, is less than everything else. So you can start whenever you want and finish the activity A1 before everything else. So when you finish the activity before everything else, you have better chance of including the next activity without a problem, right? So simply assign T to be A1. The activity A1 will always happen. There will not be any problem. Okay. Now what? Next, what can you do among the activities A2 to AN? And you have to look at the activities in that order. Okay. First you check A2, then A3, then A4, then up to AN in that order. Why is the order important? That is because we have taken this order of finish times. Okay. The activity which has the smaller finish order needs to be checked first. The activities which finish earlier have to be checked earlier. Okay. So next, among the activities A2 to AN, find the smallest I. Find the smallest integer I. Or let me see. Let's say activity. Anyway, understand? Only one. This should be compatible with the activity before. That's all. So compatibility is F1. But the first activity should have finished before starting this activity. So F1 less than or equal to SI. So the activity 1 finishes and activity I can start. Okay, and you're looking for the smallest one in the list A2 to AI. The, the earliest activity that you can choose. That is it. What do you do? This AI, you will choose it. Then assign T is equal to whatever was there in before in T union AI. Because that is your next activity, you will include that as the next element in your list, in your set, in your schedule. Alright. So assign T equal to T union AI. What do you do? Now repeat by looking at which activities. Well, when you assign A1, then you look at the remaining activities A2 to AN. Right? Now when you look at AI, the activities to look for are the ones that are greater than that now in this list. By looking at now AI plus 1 up to AN. Okay? Keep looking. At the end of this process, the list that you have T, the full set T that you have, that is your best possible schedule for accommodating activity. That's your best possible list. That's your solution to the activity selection problem. All right. As simple as that. And let's write the proper algorithm. Proper algorithm we have written actually most of it. We just have to be a little more careful. Okay. So what is the input here? So okay. So let's call this activity selection. What input do you have? You have the input A1 to AN. Okay. The list of activities A1 to AN. So now the usual way start stop. We have done all these things before. Your whole algorithm is in between. Okay. What is the first thing to do? Exactly what we did here. Okay. So one thing I don't want you to sort. One step is if the finish times are not sorted, then you have to sort them. But let us assume. Okay. So always assume that the finish times are sorted in ascending order. So you don't have to sort them. Okay. Assume that they are sorted. What do you do? You just say in the first step that T equal to NTC. Right? That's your first step with your T. Now, if K equal to 1. Why K equal to 1? We'll see. Okay? You have to keep a track of these things. So, right? So, let's do two things. Anyways, we know that A1 is included. So, let us include A1 here. So, we'll save one step. Okay? T equal to A1 and K equal to 1. Now, now you need to look at activities from the next element, right? 2 to n or 3 to n, right? So while as long as there is a next activity to look at, k plus 1 is less than or equal to n. K plus 1 less than or equal to n. What does it mean? There is a next activity to look at. So if k becomes n, you stop because you cannot go any further. So as long as k plus 1 is less than or equal to n, right? What do you do? Think about it for a moment. This is what you have to do. Find the activity AI such that F1 is less than or equal to SI. Right? So just keep doing it. Okay. So first of all, let's take k equal to k plus 1 because we now want to deal with that thing. Okay. If let m is equal to k, so m stores the position of the previous element that is selected, and now we can select the next element. Okay. So now if fm is less than or equal to, so I do m equal to k and k equal to k plus 1. If mfm is less than or equal to sk, then I say t equal to t union ak. Then I know t equal to t union ak, and then I just do so that's it. And if if not, I don't do anything. I just add k equal to k plus 1. Okay, so I do m equal to k, then I increase one value, check that with the previous one. If it is compatible, include that in the list, otherwise go ahead, ahead, ahead. Okay, what is remaining here? Well, if it is compatible and I include it, I don't want to right away and increase this because that will mess up this calculation. K plus 1 will increase 2 times. So I don't want to do that. I want this k plus 1 only when I am not adding an element. Okay, so this is not really end if. I'll write else. Okay. And if I add an element, I want to come out of uh, the if loop. So I'll just put a break. Okay. So if I add, then I break out of the loop. Yeah, and then I go back. Otherwise, I say k equal to k plus 1. Out of the loop, this is out of the whole if else condition. So, giving proper spacing, this is end. If I add the element, I break, come out of the if, then go back to the bird. And then again plus. But if it is, then I just break. I don't do this, I just go back and assign. Okay, so just work it out. It will actually be exactly what we are doing here. Okay. And finally, what do we do? Nothing. This is the end of it. End by and simply return the list. Okay, that's all. That's about the algorithm. So just go through this once and make sure that, or take an example, take 10 activities, give them some finish times randomly, and work through this algorithm and see that it is working. It is doing exactly what this is asking you to do. All right. So can you do this? Yeah. So that is the activity selection problem. There is one more question that I want to talk about. It's called the unit distance problem. What is a unit distance problem? Unit distance problem is extremely similar to it. So here now we are given n real numbers x1 to xn. Real numbers. And let's assume they are in order. So x1 less than x2 less than xn. Okay. The question is find the smallest set of closed intervals, each of unit length. such that every element xi is included in some interval. That's all. Okay. So let's set up closed intervals of unit length such that every element xi is included in some interval. It should get covered by this. So how do we do? Now I'll give you the algorithm description and you try writing it down. So I'm going to be able to write anyways. Okay. So very simple. You are allowed to take intervals of length 1. You want to take as few or as small number of intervals as you can and cover everything. Right? And x1 to xn are increasing. So no element to the left of x1 is required to be covered. Right? So you always choose the first interval as x1 to 1 plus 1 because you don't need this interval to go any left. Right? Now what do you do? Now within this unit distance, there could be some other x's, some few other x's that are included. Some of them possibly not included. Right? So what do you do now? Simply, now this is very similar to what you were just discussing before. Find the smallest xi such that the smallest xi I greater than 1 such that xi is not in this interval. So xi is greater than x1 plus 1. That's all. Because everything up to xi minus 1 is actually less than or equal to x plus 1. But they are greater than or equal to x1. So they are all included in this interval. You don't have to include them at all. So find the smallest xi greater than 1 such that xi is greater than xi x1 plus 1. And then include the interval xi plus. Okay. Now what? Now the same thing. Okay. Now you should be able to guess what you're doing. Now repeat the same for all the xj j greater than I. Look at all xj j greater than I. Find the smallest one such that xj is greater than xi plus 1 and keep include that interval. Keep on repeating. At the end, the final list of intervals that you get. Okay, so these intervals are going to be the final set that you get. That is your correct answer. That is the best possible answer. Smallest set of intervals that covers all these real numbers. Okay, that's all there is. Very, very similar to what we just did. So the algorithm is an exercise. Okay, this you should be able to do on your own. Yeah. So that's it. That's all I had to say. So I'll stop here. What you should do is, in fact, I'll probably either give you this or I'll maybe give you a snapshot of the algorithm. Go through these two descriptions again in the video. Okay. And then write down these algorithms. They are your exercise. And I want you to write them down in the assignment that I have already given you. These questions are there. All right. So yeah, that's it. So I'll stop here now. And that's it. We are done with it. Nothing more is there. This was the last video that I wanted to share. Okay. So we'll stop here now. Thank you. And good luck for the exams.